Electromotive force, also called EMF, is the voltage developed by any source of electrical energy such as a battery or dynamo. It is generally defined as the electrical potential for a source in a circuit. A device that supplies electrical energy is called a seat of electromotive force or EMF. EMFs convert chemical, mechanical, and other forms of energy into electrical energy. The product of such a device is also known as EMF. The word force in this case is not used to mean mechanical force, measured in newtons, but a potential, or energy per unit of charge, measured in volts. In electromagnetic induction, EMF can be defined around a closed loop as the electromagnetic work that would be done on a charge if it travels once around that loop. For a time-varying magnetic flux linking a loop, the electric potential scalar field is not defined due to circulating electric vector field, but nevertheless an EMF does work that can be measured as a virtual electric potential around that loop. In the case of a two-terminal device which is modeled as a Thevenin's equivalent circuit, the equivalent EMF can be measured as the open circuit potential or voltage difference between the two terminals. This potential difference can drive a current if an external circuit is attached to the terminals. Devices that can provide EMF include electrochemical cells, thermoelectric devices, solar cells, photodiodes, electrical generators, transformer and even Van de Graaff generators. In nature, EMF is generated whenever magnetic field fluctuations occur through a surface. The shifting of the Earth's magnetic field during a geomagnetic storm induces currents in the electrical grid as the lines of the magnetic field are shifted about and cut across the conductors. In the case of a battery, the charge separation that gives rise to a voltage difference between the terminals is accomplished by chemical reactions at the electrodes that convert chemical potential energy into electromagnetic potential energy. A voltaic cell can be thought of as having a charge pump of atomic dimensions at each electrode, that is, a source of EMF can be thought of as a kind of charge pump that acts to move positive charge from a point of low potential through its interior to a point of high potential. By chemical, mechanical or other means, the source of EMF performs work dW on that charge to move it to the high potential terminal. The EMF of the source is defined as the work dW done per charge dQ equals dW dQ. Around 1830, Michael Faraday established that the reactions at each of the two electrode-electrolyte interfaces provide the seat of EMF for the voltaic cell. That is, these reactions drive the current and are not an endless source of energy as was initially thought. In the open circuit case, charge separation continues until the electrical field from the separated charges is sufficient to arrest the reactions. Years earlier, Alessandro Volta, who had measured a contact potential difference at the metal-metal interface of his cells, had held the incorrect opinion that contact alone was the origin of the EMF. In the case of an electrical generator, a time-varying magnetic field inside the generator creates an electric field via electromagnetic induction, which in turn creates a voltage difference between the generator terminals. Charge separation takes place within the generator, with electrons flowing away from one terminal and toward the other, until, in the open circuit case, sufficient electric field builds up to make further charge separation impossible. Again, the EMF is counted by the electrical voltage due to charge separation. If a load is attached, this voltage can drive a current. The general principle governing the EMF in such electrical machines is Faraday's law of induction. Notation and units of measurement. Electromotive force is often denoted by or. In a device without internal resistance, if an electric charge Q passes through that device, and gains an energy W, the net EMF for that device is the energy gained per unit charge, or with Q. Like other measures of energy per charge, EMF has SI units of volts, equivalent to joules per coulomb. Electromotive force in electrostatic units is the Stach volt. Formal definitions of electromotive force. Inside a source of EMF that is open-circuited, the conservative electrostatic field created by separation of charge exactly cancels the forces producing the EMF. Thus, the EMF has the same value but opposite sign as the integral of the electric field aligned with an internal path between two terminals A and B of a source of EMF in open circuit condition. Mathematically, where EC is the conservative electrostatic field created by the charge separation associated with the EMF, D is an element of the path from terminal A to terminal B, and denotes the vector dot product. This equation applies only to locations A and B that are terminals. It does not apply to paths between points A and B with portions outside the source of EMF. This equation involves the electrostatic electric field due to charge separation ECs and does not involve any non-conservative component of electric field due to Faraday's law of induction. In the case of a closed path in the presence of a varying magnetic field, the integral of the electric field around a closed loop may be non-zero. One common application of the concept of EMF, known as induced EMF, is the voltage induced in such a loop. The induced EMF around a stationary closed path C is where now E is the entire electric field, conservative and non-conservative, and the integral is around an arbitrary but stationary closed curve C through which there is a varying magnetic field. This definition can be extended to arbitrary sources of EMF and moving paths C, which is a conceptual equation mainly because the determination of the effective forces is difficult. Electromotive force in thermodynamics. When multiplied by an amount of charge dz, the EMF yields a thermodynamic work term dz that is used in the formalism for the change in Gibbs energy. When charge is passed in a battery, where G is the Gibbs free energy, S is the entropy, V is the system volume, P is its pressure and T is its absolute temperature. The combination is an example of a conjugate pair of variables. At constant pressure, the above relationship produces a Maxwell relation that links the change in open cell voltage with temperature T to the change in entropy S when charge is passed isothermally and isobarically. The latter is closely related to the reaction entropy of the electrochemical reaction that lends the battery its power. This Maxwell relation is: if a mole of ions goes into solution, the charge through the external circuit is, where N0 is the number of electrons, ions, and F0 is the Faraday constant and the minus sign indicates discharge of the cell. Assuming constant pressure and volume, the thermodynamic properties of the cell are related strictly to the behavior of its EMF by, where ΔH is the heat of reaction. The quantities on the right all are directly measurable. Electromotive force and voltage difference. An electrical voltage difference is sometimes called an EMF. The points below illustrate the more formal usage, in terms of the distinction between EMF and the voltage it generates. For a circuit as a whole, such as one containing a resistor in series with a voltaic cell, electrical voltage does not contribute to the overall EMF. Because the voltage difference ongoing around a circuit is zero, the EMF is due solely to the chemistry in the battery that causes charge separation, which in turn creates an electrical voltage that drives the current. For a circuit consisting of an electrical generator that drives current through a resistor, the EMF is due solely to a time-varying magnetic field within the generator that generates an electrical voltage that in turn drives the current. A transformer coupling two circuits may be considered a source of EMF for one of the circuits, just as if it were caused by an electrical generator. This example illustrates the origin of the term transformer EMF. A photodiode or solar cell may be considered as a source of EMF, similar to a battery, resulting in an electrical voltage generated by charge separation driven by light rather than chemical reaction. Other devices that produce EMF are fuel cells, thermocouples, and thermopiles. In the case of an open circuit, The electric charge that has been separated by the mechanism generating the EMF creates an electric field opposing the separation mechanism. For example, the chemical reaction in a voltaic cell stops when the opposing electric field at each electrode is strong enough to arrest the reactions. A larger opposing field can reverse the reactions in what are called reversible cells. The electric charge that has been separated creates an electric potential difference that can be measured with a voltmeter between the terminals of the device. The magnitude of the EMF for the battery is the value of this open circuit voltage when the battery is charging or discharging. The EMF itself cannot be measured directly using the external voltage because some voltage is lost inside the source. It can, however, be inferred from a measurement of the current ion voltage difference V, provided that the internal resistance R already has been measured, equals V plus IR.